It's a real pleasure to introduce our next speaker, Francesco Sette. Francesco received his PhD in physics from the University of Rome after, I believe, he spent almost a decade at Bell Laboratories, where he really began to develop innovative new tools and methodologies for synchrotron radiation-based research, and made a tremendous impact in areas including high-resolution soft X-ray spectroscopy. Francesco joined the European Synchrotron Radiation Facility, ESRF, in 1991, became a group leader where he really developed a new generation of inelastic X-ray scattering beamlines that really made possible the study of atomic motion and electronic properties of matter in unexplored regimes. In 2001, Francesco became the research director of ESRF, and since 2009, he's been the ESRF Director General. Let me say that if you look at what Francesco has accomplished at ESRF as a leader, it's been absolutely astounding. His vision and bold look at the future of ESRF has laid the foundation and has seen the implementation of an upgrade program, which really has provided the foundation and the platform for another decade of discovery and innovation and excellence in synchrotron science at ESRF. So it's a real pleasure to welcome Francesco, and he's going to talk on next generation X-ray analyses.
Thank you. Thank you very much, Keith. Thanks to all of you for listening to me in the next half an hour. That's better? Better? It's okay? Okay. And in particular, thanks to SLAC for inviting me in this event. Yes, I started my career in Italy, but the real start was here at Stanford in 1981 on the Grasshopper and the Jumbo beam lines. Somebody remembers that with Joe. I was a postdoc with Joe Storr, who's on the audience. So I thank also very much the previous speaker because introduced a lot of concept on which I would be able to skip because what I wanted to show you is that indeed the X-ray analysis, in particular X-ray analysis based on synchron radiation, gave a very important contribution during the last 40 years. And I believe they will continue to do so. Here. No, it's this one. Okay, so this doesn't seem to work. All right, so the point I'm going to touch is X-rays and synchron radiation. So I will concentrate on X-rays. Then a little bit about the science that is going on and what we may see in the coming years. And then a word more from a facility point of view of potential upgrades and how in places like SLAC, for example, we could do things even better. So X-rays, you know, when we talk about X-rays, this is what most of people think. This is how you're going to look at your luggage when you take an airplane or when you take a chest X-ray. Yes, this is indeed a very important use of X-rays. And you do that with this kind of machines, which are called a rotating anode, in which you have a filament producing electrons that are accelerated and bombarding a cathode that rotates not to get hot. And then you produce your X-rays. And for example, with synchrotron, you imagine you can do things much better. For example, I'm going to give you as an example here, if you want to know if a battery is empty or is still charged, well, there are many ways of doing it, and an expensive way is to go to a synchrotron and and to take a tomography of this battery. But you already see that there is a lot of details, and for example, you understand why it's very difficult to recharge a battery, because you have to bring the structure from what it was to what became after being empty. So this already tells you that maybe this synchronous experiment is useful to really get into the understanding of the material, I would say at the microscopic, but then the big step is nanoscopic level. And in fact, you can do things which are a little bit more fancy. For example, this is an example of studies associated to how you coat a stainless steel vessel with tungsten. This is the ITER vessel. and then you can go to a synchrotron, and you can really do a very careful analysis with resolutions that now are well into the microns or submicrons level, to identify the quality of your coating, identify the tungsten parts, the pores, and where the interdiffusion of the materials, and so on. So these are the kind of things that you want to think of, but basically the aim of the talk is to really show you that today I believe that this is really a unique way to investigate materials that complements other techniques, but is quite unique. And in fact, we just heard that the technology and the challenges that our society is facing are strongly linked to discovery of new materials, but this has been the case all over humanity. I mean, it's not a fact that every period of human age was, in fact, identified with a material starting from the Stone Age. So what is the age? Well, I think the previous speaker introduced it extremely well. It's, I would say, the age of knowledge-based materials, in which a very detailed knowledge of the structure, the size, the components of your materials are linked to the function that you want to have of those materials. And then through, indeed, the simulation, this was Helmut's question, you really want to try to even optimize or to create new functions, and then there is the processing, how you're going to make these materials. And this brings you, to this sort of tetrahedron in which structure, properties, performances, and processing are all linked together. And a key element to go on is the characterization of the different steps, and in particular of this step and the step of processing and the characterization of what you have been processing. And that's where the processing tools comes in. And of course, you have excellent tools available for that in laboratories. But when you increasingly need techniques with nanometer spatial resolutions and many other features like bulk, surface, and interface sensitivities, chemical and magnetic information at the atomic and atomic bonding level, time evolution from millisecond down to the molecule bonding and electron motion times, well, on top of that, possibly non-destructive, that's where you come to these large-scale facilities like thermal neutrons, reactors, spallation sources, X-rays at storage rings, and free electron lasers. So this, I think, is for me an extremely important point that pushes me to do what I'm doing, because I really believe that these large-scale facilities are a key element for the progress in our future understanding of materials. So I don't have to tell you what X-rays are. Where synchrotrons operates in this X-ray region where you have continuous and bright operation of X-rays in wavelengths which are comparable with the interatomic distances, and that's what makes X-rays unique. That as electrons today are the ideally suited tools to achieve a sub-nanometer spatial resolution. So you will not suffer from diffraction, which is the problem of visible light as soon as you go below 500 nanometers. And already with X-ray synchrotron and nano imaging, resolution of the order of 10 by 10 nanometers have been achieved quite routinely. And there are reasons to believe that this can be further pushed down. So I'm not going to make a long story about X-rays. But 2012 is, of course, the 50 years of SLAC, but it's also the 100 years of the discovery of diffraction from Max von Laue in 2012, and he received in 1914 Nobel Prize, followed by Bragg in 1915, and by the way, in 1901, Röntgen received the first Nobel Prize for physics. So that's what you do with X-ray tubes, and as you can see, since the Röntgen time over almost 100 years, there was no major improvement in the source. Then there was, these other ways of producing radiation, which is by submitting relativistic electrons to an acceleration. And this is the famous picture of the General Electric team that in 1947 built a synchrotron, a 70 MeV synchrotron. You see here the vacuum tube in which the electrons were supposed to circulate, and then indeed they circulate, being curved by the magnets that you can see here. And this was the first observation of synchronal light that has all high energy physicists in this room know are more of a nuisance than anything else. In fact, it's one of the major ways to lose energy for electrons in a high energy circular beam. But the real change came when the idea of storage ring came up. This came up in 1960 with Bruno Tuschek, and the first storage ring with this little object that was built in Frascati. And out of that, then there was everywhere a lot of activities in building storage rings, and many other people thought that indeed that this storage ring could also be used as a source of light. And this is the SSRP projects, and here we see the three guys that were really associated with that, and I look forward to say hi later on in the day. And I also took the occasion to mention that in fact the second generation of storage rings came when synchronal radiation science became to have such an impact on the material science community that facilities were started to be built just for that purpose, using a bending magnet radiation. And the first dedicated source for synchronal radiation was Tantalus 1 from Ed Rowe, and again in the United States, and this was in 1968. And finally, we come to today with the third generation sources that are based on the extensive use of insertion devices, wigglers and ondulators. And as you can see here, there has been a steady increase in the brightness of the beam. And if you compare with the X-ray tubes, we have now achieved today something of the order of 10 to the 100 billion times brighter sources than a laboratory source. And so that's what indeed makes synchronal radiation so unique. Of course, the size has also gone up, and the cost associated with it. This was ADA, and this is the ESRF. And as the ESRF, many other sources all around the world have been built. And you can see here the most recent and most modern source. They are mostly concentrated in the northern hemisphere, but also the southern hemisphere is starting to catch up. In fact, the story is not finished. We have hard X-ray sources in the US, in Chicago, at the ESRF in France, Spring 8 in Japan, Petra 3 also in Europe. New synchron sources like Soleil, Diamond, and Petra 3 came up quite recently, also SSRF in China, in Shanghai, and Alba in Spain. And there are plans for new one to come in the forthcoming years, and also plans for new other sources that are not yet under construction. So as you can see at the world level, there is a very, very active activity for synchronal radiation. And the reason is that this tool is so broad and gives a contribution to many areas of science, not just the characteristic hard sciences like solid-state physics, chemistry, medicine, and life science to investigate matter, materials, and living matter. But more and more you find applications of synchronal radiation science in more applied scientific areas like engineering, material science, earth science, environment, cultural heritage, and so on. And here I just want to also mention that the service produced by this facility is not only addressing a lot of users, but it's also very, very productive. This, as an example, is the publication records of the ESRF over the last 16 years. And as you can see, we have something like 2,000 refereed publication every year. If you take the total, it's more than 20,000 in 16 years. And if you look just at the high impact publications, they are of the order of 200 publications per year. You have a paper on Nature or Science every 2 weeks, roughly, in average. So let me now switch a moment to the science. This brighter beam, for example, has now allowed to start to use coherence also in the X-ray regime. And very quickly, you know, by having a small opening, you can select the coherent flux, and you illuminate your sample, and you look at the diffraction of your sample, and by technique of reconstruction by iterative phase retrieval, oversampling, and so on. And we'll hear much more in the talk today, later on today, on the application of X-FEL. This is a very interesting technique that could allow us to have, in fact, resolutions of the order of 5 nanometers. This has been obtained on very favorable conditions on gold particles, but you can see here that it's really at the limit of the statistics, and this is just because we are flux limited at this stage. So there is a real need for even brighter beam. I want to continue to show a more complete example in which you are able to do using phase contrast, nanotomography, so a three-dimensional reconstruction of objects with nanometric resolutions. And this is using this technique of zoom do a nanotomogram on objects which are off focus. And then this allows you to keep the sample preparation very straightforward. And the magnified phase contrast imaging allows you for quantitative reconstruction of electron density and also gives you very high sensitivity. And this has been applied to a solid oxide fuel cell. These, as you know, are high-performance electrochemical devices. And today we are looking at them a lot for energy conversion. They have advantages like reduced greenhouse effect. They are made of ceramic materials, and as a consequence of that, they operate at very high temperature, typically about 800 C, and this is one of the main problems for their use. And for that reason, they are, yes, very efficient, but they also go through rapid degradation, and the reason is for this high T operation. So you have residual stress, Lemons diffusion, the evolution of the microstructure, and so on. So here you clearly see the need of a tool that would allow you to study this kind of effects. And indeed, this is what can be done today. This is a sample out of the tomogram of the order of 100 microns, but the resolution here is of the order of 50 nanometers. So the voxel side is 25. And the kind of information is, for example, this is the anode, that you can fully determine the porous network in the hydrogen electrode, possibility to calculate the gas diffusion and the transport in the anode. So these are key elements to understand the properties of the materials and to simulate how you can make it better or make it more efficient. And these are the kind of pictures that you have. This is through the cell. This is the cathode. This is the yttrium-supported zirconium, which is the electrolyte. And this is the anode substrate. And you can really make this three-dimensional reconstruction. This is a reconstruction of a cube of 36 times 3 power 3 cubic microns. And you have, you know, the red is the nickel particles, the white is the electrolyte, and the blue are the porous. So you can see the level of and the quality of picturing that you can create. Also was mentioned in the previous talk that you know, nanoparticles are increasingly used in applications, but this also raises concerns about their potential negative environmental and health effects. So again, the need to develop tools that allows you, for example, to know where nanoparticle goes after they have been used, how they accumulate, how can their isolation or how our immune system may react to their presence. And again, these are the kind of things that you can do. For example, this is a study of the fate of cobalt, iron, oxygen nanoparticles that were injected into a mouse of fibroblast cells. And the idea was indeed to see where these nanoparticles will accumulate in order to evaluate the cytotoxicity of nanoparticles to be used. They are used as a drug delivery vectors or imaging contrast agent. Look at their perinuclear localization, interaction with the cell metabolism, and so on. And here what you do is, again, a nanoscopy with an X-ray nanoprobe, but instead of doing a tomography, you do a kind of microscopy where you detect the fluorescence of specific chemical elements. This is the calcium that you can see is concentrated in the perinuclear region, the iron as well from the nanoparticles, and this is the phosphor that is in fact spread over all the cell as a reference. Similar things, this is, for example, uptake of carbon nanotubes in macrophage. The macrophage are the cell that are associated with the immune system in humans in order to detect all those biological material that is not useful or not necessary. And again, inside the carbon nanotube, you have iron markers. So you can see here that indeed the carbon nanotubes goes inside the macrophage. So these are also other kind of applications. And I want to finish with a third one, which is another, I think, quite beautiful application of synchron radiation during the last few years, is the study in paleontology, studies that allows us to look at the treasure of our past. This is a study on a fossil that has been found in South Africa and corresponds to an age of about 1.9 million years, and is thought to be a new hominid species, and is indeed perhaps thought to be one of the missing links between the Australopithecus and the Homo genus. Again, if you look at what you can do in a hospital with a CT machine, which you standardly find in a hospital, this is the kind of pictures that you have. If you go to a synchrotron, this is how your quality improves. And indeed, when you do the three-dimensional detection, you can see here you have an object which is about 10 centimeters in diameter, even a little more, and you can non-destructively fully determine the internal shape of this unique fossil with submicron resolution. And there's a lot of studies that can be carried out, for example, on the structure of the teeth and so on. And one of the outcomes that came out from the study is a very precise determination of the area in which the brain could be placed. And in fact, from the size of the brain of this object, of this fossil, there are very strong indications that, in fact, this is most likely an ancestor of the Homo genus. In fact, out of this work on these fossils on September of last year, we had 5 science papers all together on the brain, the hand, the hip bone, the foot, and the ankle. So it's quite amazing. Let me give you another quick example on how these tools are being used. This is, for example, again, a study on malaria. You know that malaria is indeed still a big killer. We have something like 300 to 500 million clinical cases per year and about 1 million deaths. Resistance has been developed of the main parasite towards existing drugs. So there is a constantly upgrades of drugs for malaria. Malaria drugs, starting from the first one, which is the famous quinine, have all this double ring as a leitmotif. These are all different kind of anti-malaria drugs that have been developed over the years. Recently, new ones have been developed where there is still the double ring, but also we have now the presence of an iron ring. And if you look at how the malaria parasite attacks the blood cell, is sort of summarized here. You see here a blood cell, and you see the parasite that basically attacks the cell by feeding himself out of the hemoglobin. And by feeding himself, what he does, it creates these hemozoin crystals where basically all the iron from the hemoglobin is accumulated. And in fact, the creation of this crystal is a way for the parasite to survive, because if this iron will stay within the parasite will be poisoned and will die. So the target of most drugs is to avoid this hemozoin crystal to grow. And the ferroquine, which is this new family of drugs that has been recently developed, is thought to be a more efficient and new way to stop the growth of this crystal. And in order to understand if this is indeed the case, because iron is everywhere in the hemoglobin, an analog of the ferroquine using ruthenium at the place of iron has been made. And as you can see here then with this nanofluorescence imaging, where you can image different elements, here you see chlorine, here you see the iron, you see the hemozoin crystal plus iron from the hemoglobin inside the blood cell. And then if you look at the ruthenium, you can clearly see that the ruthenium is completely concentrated around these hemozoin crystals. So this clearly is a way to directly show the effect. And I just want to finish with two very quick view graphs saying that perhaps one of the biggest successes of synchron radiation over the last 10 to 20 years is its contribution to the development of structural biology and to the contribution of structural biology to biology in general, and indeed perhaps the most important result, or the results that summarizes all the work that has been carried out by many scientists during this period is the work on the ribosome that received the Nobel Prize and has been given to three groups, the groups of Ramakrishnan, Stites, and Jonath, for the determination with atomic resolution of the two subunits of the ribosome. So in the remaining few minutes, I want to just talk one moment about what's next, upgrades of existing source and future storage rings for synchron radiation. Many plans are going on, in particular at the ESRF, APS, and Spring 8, but also there are plans for completely new sources. Well, the aim is always, I would say, the same, to try to deliver new and better conditions for new and better science to our users. So I think that in this area, the user aspect of this facility is a key element for their success. But another important aspect, and which will be even more important in the coming years, is the ability of this large-scale facility to attract young people and to ensure that this big investment that are made for the future, for a future to come of at least next 20, 30 years, there is enough young people that can indeed then continue to efficiently use these facilities. So when we talk about better science, when we talk about science in the materials, in the living matter, and so on, it's clear that there are very fundamental scientific programs like the one that were discussed before on nanoscience, but also in the area of structural biology. But all of them are obviously very strongly linked to societal challenges and to the development of new key materials. So today it's really very important that we link the upgrade of these facilities to areas like advanced materials, health and life science, and energy research, and in fact instruments which are brighter, more powerful, and stable for this users community really address areas like nanoscience and nanotechnologies. I didn't talk too much about pump and probe experiment and time-resolved science, so we will hear more later on. The X-ray imaging of the nano world, I think this is really a key aspect. I think X-rays have the possibility to arrive almost or maybe even to atomic resolution, and therefore becoming a tool very complementary to electron microscopy techniques, structural biology and soft matter, and also science at extreme conditions, which very often are a unique niche for X-ray analysis. So in these upgrade programs, one can recognize 4 areas of upgrade. The most important is, as usual, I would say the accelerator and source upgrade, because major changes and qualitative improvement in the science has always come from better accelerators. And the areas are being discussed are stability and reliability, increased brightness, timing and time resolution down to the picosecond time scale. This now I refer explicitly to storage ring. New state-of-the-art of beamlines, enabling technologies, better optics, better detectors, precision micro and nanomechanics if you want to study nano object, and more importantly, data handling, real-time analysis, and storage, and also automation and remote control. The fact that more and more these instruments could be used directly from the lab of our users, and therefore get them much more integrated into the laboratory activities. And very often this requires also big investment for creating a new experimental hall and new premises for these new instruments. So at ESRF we have launched in 2009 an upgrade program. We have a phase 1 which has been mostly centered on improving beamlines, but also accelerators and enabling technologies have been improved. And now we are in the process to look into a new phase, a phase 2, which is under preparation. And in particular, this new phase look to a major upgrade of our accelerator source. And I show you here very quickly 3 view graphs that I received from our accelerator and source division. I don't go into the details, but this is the lattice that the ESRF has today. Is a lattice that provides an horizontal emittance of 4 nanometers. And plans are to go to a new machine with an upgraded and reduced horizontal emittance. That is reduced by almost a factor of 40. This simulation here shows 0.13 nanometers, and you go from a double band achromat to a 7-band achromat. These are the electron beam size characteristics. So you see today we have 2 kinds of lattice which are compenetrating, high beta and low beta. In the new there will be only 1 lattice. And as you can see, the source size in the horizontal direction will go down to 28 microns, and the divergence to 5 microradian. If we look at the effect in terms of brightness, this is summarized here with optimized ondulators at low energy. We will have an improvement of about factor 16. In the X-ray region of about 10 kilovolts is a factor of 30, and then the harder region of something like 60 kilovolts of a factor of 36. And this is obviously a very important improvement for all those nano imaging approaches that I was showing before that will enable extremely new possibilities. I also want to mention that out of these studies that is aimed to see whether one can have a fully diffraction limited source, studies have been also carried out not only for 150 picometers horizontal emittance lattice, but also for 10 picometers. And as you can see here, the brightness down to something like 100 picometers scales more or less proportionally to the horizontal emittance. But when you go below 100 picometers, the gain goes more or less as the square root of the emittance reduction because of the effect of diffraction limits in the source that starts to be observable. So this is somehow the holy grail on which the ESRF is working today and is opportunity to substantially reduce the storage ring horizontal emittance. And compared to what we have today, the brilliance and the coherent flux increase is about a factor 40. The total power on beamlines optics is substantially reduced. The power density increases by roughly a factor 2. The electrical consumption of this machine is also substantially reduced. More than 90% of the existing infrastructure is maintained in use, and they will require about a 12 months shutdown for its implementation and commission. So with that, I hope I gave you a flavor that 40 years of work have gave to us and to the synchronon user tremendous tools in the areas of material science research and research on living matter. During the last 40 years, synchrotron sources have improved by something like 10 orders of magnitudes, and if you just look at third generation sources, over the last 15 years, they improved something like a factor 3 order of magnitudes. And I also hope that I show you that X-rays from synchrotrons are a unique tool for the study of nanomaterials. And in order to continue to be useful and to be maybe even increasingly useful, you need to have this facility to continue to be powered by scientific excellence, but most importantly, they must maintain a faithful and committed user service. And I believe that SSRL here was probably the first synchronous radiation source in the world that really took that as a key, as a must for its operation. And I always took SSRL as an example for the way and the transparency in which the facility was operated vis-a-vis to the users community. To enlarge the users community, and with that I also believe that we are coming to a time in which these facilities are something that is more than photons. In other words, it's true that a facility has to deliver these fantastic beams, but also has to provide a support that is in sample environment, data analysis, data storage, optics, and so on. And all this aspect can come from the facility. But when you come to sample environment, to specific scientific areas, then you cannot rebuild the old research lab existing in the world around the synchrotron. So we need to find ways to attract and to build that infrastructure that is necessary to use this facility at their best. And in that sense, for example, the work that is being done at DAISY, and in particular around the XFEL facility, to really attract key scientists and key players in order to use the most efficient, in the most efficient way, the X-ray facility is something that probably should be looked at for synchro radiation source of tomorrow. And finally, there is this quest for the future storage ring synchronous radiation source. During the last 20 years, there's been a lot of development in accelerator science, and the possibility of having improved horizontal emittance to go to a fully diffraction limited beam are there. One can, in principle, conceive today a greenfield facility with this kind of characteristics. This will give at least another 2 orders of magnitudes in brilliance to the facilities. and therefore the possibility to push this curve even higher. And therefore, with that, I think there is still a lot of opportunities to qualitatively enhance synchrotron science, and I am convinced that the SLAC will continue to be one of the leading actors in the world in this area. And with this, I thank you for your attention.
Okay, open for questions. Raise your hand. I see Herman in the back. Take it, Herman. Yeah.
Thank you, Francesco, for this wonderful summary of the field. I'd like to mention, you pointed out the many new sources that are underway, being built in Brazil, Korea, Taiwan. Another one of these that's particularly interesting is the Sesame project, which is under construction in Jordan now as a collaboration like CERN among 9 countries in the Middle East, which are building this third-generation machine in Jordan. And if you're interested, it's on www.sesame.org.jo. I encourage you to look at that. I'd also like to make 2 brief comments on the early history of synchrotron radiation that you mentioned. You pointed out that the first visual observation of synchrotron radiation was at the General Electric 70 MeV synchrotron in Schenectady. It should be pointed out that that was a totally serendipitous observation because that machine had a glass vacuum chamber. But 2 years earlier, John Blewett, who was working on a 100 MeV Betatron at General Electric in 1945, was reading the papers by Ivanenko and Pomeranchuk, the Russian theorists, who pointed out that there should be this radiation when you get to energies of 10s or 100 MeV, and he had a 100 MeV machine, and he looked for this radiation, but the vacuum chamber of his Betatron was opaque. He couldn't see anything visible. He tried to find it with antennas outside and failed, but then he realized that the amount of energy lost is significant, and this would cause a contraction of the orbit, and he could measure that with the beam diagnostics that he had inside the vacuum chamber, and showed that it was exactly comparable or exactly equal to the amount of energy lost due to synchrotron radiation. I think that's the first real observation, if you like, an indirect one. Lastly, you mentioned that the first storage ring to be used for synchrotron radiation was the Tantalus ring, 240 MeV ring in Wisconsin in 1968, due to the vision of Ed Rowe and colleagues that made use of a leftover R&D 240 MeV storage ring from the Mura project, Midwestern University Research Association. But the first storage ring to actually be built as a light source and not taking advantage of existing facilities from high energy physics was the Japanese machine, the SOR, the Synchrotron Orbital Radiation Ring at the University of Tokyo, led by other visionary people, Taizo Sasaki and his colleagues there, who got this first second-generation ring operational in 1974, 300 MeV, small storage ring, but the first one to be conceived of and started and built and used as a dedicated light source from the beginning. So thank you very much.
That was in 1974.
74 was its first operation.
Tantalus was 1968.
Yes, okay. But
So it was the first dedicated storage ring.
yeah, I know, I wasn't contesting that. I'm just pointing out that that it was the Japanese who realized the need for doing this.
Jordan was in the list.
All right, we have another question, please.
I look for it.
Anyone else? Wave your hand high. Okay, Claudio.
I also would like to point out that synchrotron radiation is a bridge between science and the humanities. The work done on the Archimedes manuscript. And you go to the Getty Museum in Los Angeles, they use X-rays to look at paintings, sculpture, ceramics, every day. So it's really a bridge also between us and our colleagues on the other side of the campus.
If you have time, I can give you a half an hour lecture on that.
During the coffee break, we'll have Yes. Middle here. Somebody get a mic down. Lori. She's coming.
Would you comment on the balance between synchrotron sources and neutron sources from reactors? Is the balance right for extracting the maximum science from the materials you study?
I would say yes, in the sense that indeed neutrons are another very, very important tool for the study of materials. There are all a series of applications in which neutrons are as important, if not even more powerful than X-rays for specific applications. What I do find a difficulty in future neutron science is indeed the possibility to reach submicron resolution. That is just because of the power of the source, and it would be fantastic to have a neutron beam of 10 nanometers or in that range. That will indeed be an extra tool that with X-rays and electrons will give tremendous potential to the investigation of matter.
Okay, well,